And for the next 40 minutes, we're going to be talking about the fundamentals of networking and security and the services surrounding that on AWS. So if you're already familiar with AWS and you've been in some of the previous sessions today, you will have heard about EC2 instances, virtual machines running in the cloud. So you probably are going to be running at least one of those. You might be running more than one. And all of these are running within AWS, running in the cloud. But in reality, there's a little bit more detail behind that. All of these EC2 instances are actually running inside a VPC. And that's because every single EC2 instance that you launch will need to have an IP address. And in this case, I'm showing you the private IP addresses for these EC2 instances. If we want to go into one more little piece of detail, these EC2 instances with their IP addresses are running within particular subnets, and these subnets are aligned to our availability zones. Some of these EC2 instances may also need to have public IP addresses, and as a result, you need a route to the internet using something called the Internet Gateway. So what you're seeing on the screen now is a typical VPC, an internet-connected VPC. And to start this session, I want to talk you through the process of actually building an environment like this. So simply put, a VPC is your private network within AWS, Virtual Private Cloud. So let's build an internet-connected VPC. And to do that, there are 4 really quite simple steps. The first thing we need to do is choose what IP addresses we want to use within our VPC. Once we've done that, we need to then create our subnets, which are aligned to the availability zones within the AWS region. We need to then create routing out to the internet. And then finally, we need to actually allow the traffic to flow. We need to configure the security within our VPC. So with these 4 simple steps, we can build our internet-connected VPC. So the first step, let's choose our IP address range for this particular VPC. Now, we use something called CIDR notation, that's classless interdomain routing. And this is the kind of format that it takes. Now, if you've not seen this kind of format for IP addressing before, it's quite simple. What it means is if we convert all of that into binary, it means that we take the top 16 bits and we fix them. So this particular VPC is 172.31, and then it's everything from 0.0 through to 255.255. That's the VPC that we're going to create. This is the CIDR range that we're assigning to it. When we choose our CIDR range, that's the first choice we make for our VPC, and it is fixed for the lifetime of that VPC. You can't change it once the VPC has been created. We would recommend that when you create the VPC, you choose RFC 1918 address space, that's private address space. And in general, unless you have another reason, you might as well start with a /16. That's the largest amount of address space that you can assign to a VPC. That's just over 64,500 IP addresses. I think that might be enough to get by for now. The other thing to consider when you choose this address range is if you have an existing on-premises network or a data center network already, let's choose an IP address range that does not overlap with that existing infrastructure that you already have. Let's start with a nice clean set of address space. So great, we've chosen our CIDR range for our VPC. The next thing to do is to divide that up into subnets. So here we have our VPC, and I'm going to overlay on top of that the availability zones for this particular region. So we're using EU West 1, this is in Ireland, and we have 3 availability zones in Ireland. So at a minimum, we can choose to create 3 different subnets, 1 in each availability zone. When we do that, again, we need to assign a block of IP addresses from the CIDR range assigned to the VPC to be used in each of these subnets. So in this case, I'm going to go with /24s. So 250 odd IP addresses, and we're going to assign a different /24 to each of the subnets that I've created. So as a general recommendation, when you're choosing your IP address schema for your VPC, we would suggest, unless you have another reason, to start with /16 for the actual VPC itself, and start with /24s for the subnets. You can then keep creating more subnets with /24s assigned to them within that VPC as you need to. Again, start from the perspective of having 1 subnet per availability zone, at least, but you can always grow that later on. So now we have our VPC and our subnets created. A VPC is a pretty lonely place unless we can talk to something outside it, so we want to talk to the internet. So how do we configure that? Well, within the VPC, we're going to configure routing. We're going to use route tables, and this is where interesting things happen in the VPC. A route table is simply a set of rules that explain where traffic should flow or where packets should be directed to. And when you create your VPC, you have what's called a main route table created for that VPC at the very beginning. That main route table just has one simple entry in it, which I'll show you in a moment, that allows traffic to flow just within your VPC. And we're going to need to modify that to enable traffic to flow to the internet. One thing that you can do with route tables, though, is that you can assign a different route table to every single subnet in your VPC if you want to. So you can have different routing applied to different sets of EC2 instances. But for the moment, let's keep it fairly simple. So this is the main route table for my VPC. You can see down at the bottom of the screen, I have an entry that says 172.31/16 is local. So that enables the traffic to flow within my VPC between all of the EC2 instances in the subnets. For traffic to flow out to the internet, though, I need to create one other thing for my VPC, and that's called an internet gateway, an IGW. So you can see here I've created an internet gateway in the console. It is attached to my VPC, but until I go and modify the route table, there is nothing using this particular internet gateway. So let's go back to the route table we were looking at earlier. You can see the local entry that's already there. We're going to add an entry which says, anything that is not destined for my VPC, let's send it to the internet gateway. And that's expressed as a route that says 0.0.0.0, the internet. You can get to that via IGW and the identifier for the internet gateway. So now we have two entries inside our route table. Okay, so we now have subnets and we have a route out to the internet. We're getting there, but we have one more thing that we need to configure, and that is the security for our VPC. Now, we support two primary concepts to consider here for your VPC in terms of security: network ACLs and security groups. So let's take network ACLs first. A network ACL is basically a stateless firewall. You need to define traffic flow in both directions, and you apply this to a subnet. So what you can see here is that this particular network ACL is assigned to all of the subnets in my VPC, and it has a very simple rule base at the bottom of the screen. You can see that the lowest rule at the bottom, the one that we create by default, is a deny rule. On top of that, though, when you first create your VPC, we actually add an extra rule for you, which is the rule 100 that's shown here, that actually allows all traffic. And that's because quite often this is where customers choose to start with their network ACLs. And network ACLs are processed in order of their rule number. So on the left-hand side, you see a rule number, and traffic is then matched against that rule and either allowed or denied. The translation of what you're seeing on the screen here is, as much as we have a deny rule at the bottom, above that we have an allow rule that allows all traffic. So right now, this network ACL is going to allow all traffic in and out of our subnet. But what about security groups? So security groups are applied in a slightly different way. If you look at our VPC here, we've got two very clear different sets of EC2 instances. We have these ones at the top, and we have the ones at the bottom. Now, we might consider these perhaps our web servers at the top, and maybe our backend servers, our database servers at the bottom here. And security groups tend to follow your application structure. So in this case, if we think about what we would want to happen with our traffic coming into our VPC, we want to allow port 80 inbound from the internet. These are web servers. So that's the first thing we need to be able to configure. But our backend servers, no one needs to be able to talk to those except for the web servers. So the rule that we want to apply here is allow traffic from my web servers to my backend servers on a particular port number. So this is what it looks like. But how do we actually configure that? Well, if we go and take a look at our security groups in the console, you can see the top two security groups are the ones we're going to be working with here. We have my web servers, and down at the bottom, you see the rule that I have created within this security group. And I think it's pretty self-explanatory. We're allowing port 80, TCP, to be able to connect from a source of anywhere. So traffic from the internet is allowed on port 80 to our web servers. But what about the backend servers? The backend servers, we actually said we only want to allow traffic from our web servers. So we could do that by listing all the source IP addresses of those web servers. But actually, we don't need to do that. Because we've got all of our web servers in a security group, we can reference that security group as the source. So you can see on the bottom right-hand side, it says the source of this traffic on my database port, in this case, port 2345, That is allowed from a source of the web servers. We don't have to reference any IP addresses. So this is a really easy way of configuring security within your VPC and allowing traffic to flow using security groups. So a couple of other things to consider with security groups. Always consider the principle of least privilege. If a permission is not required, don't grant it. If you don't need to open up your back-end servers to the internet, don't. Only open them up to the web servers. VPC security groups allow you to control traffic both inbound and outbound. You'll see two tabs at the bottom of the screen if you're using the console. So you can actually choose to allow traffic inbound on port 80, and because these are stateful firewalls, will allow the reply automatically. If those web servers don't need to be able to reach out to the internet, you can set the outbound rules to not have any entries in them at all. That's the best practice for a security group. And finally, you'll quite often find that the architecture of your applications map quite nicely between security groups and IAM roles. And IAM is identity and access management. So an IAM role will determine what it is that instance can do, and the security group will determine who it is that I'm allowed to talk to. So normally those two things work quite closely together. So we've now got our internet-connected VPC. What if we want to connect to something else? Well, what else might we want to connect to? Well, we might want to connect to our on-premises infrastructure, our data center. We might even want to connect to other VPCs. So how do we actually do that? Well, first of all, let's consider the fact that if we're talking to other environments, perhaps a data center, we might want to restrict our ability to talk to the internet. We might want to be able to connect this VPC to many other VPCs. And then finally, once we've done that, connect back to that corporate network. So these are the three steps that I'm going to take you through next. So how do we restrict routing out to the internet first? Before we connect this VPC to anything else, let's consider that. You'll remember earlier that I mentioned you can create route tables for individual subnets. So let's take our application here. We've got our front-end web servers again and our back-end servers. But this time, let's put them in two different subnets. What we now want to do is configure these web servers so that they can talk to the internet. Remember, we're allowing port 80 in. This is for our consumers to access our web servers. So that's fine. We've already built one of those. We have an internet gateway. We have a route table. But these back-end instances, they don't need to ever talk to the internet. So how do we configure that? Well, here's our two subnets. I've put them side by side now rather than underneath each other. We need to consider one other element, though, for our back-end servers. What if they need to go and get some updates? What if they need to reach out to a Yum repo or Windows Update, something like that? So we can use something called a NAT gateway to enable that, and actually separate our two subnets using two different route tables. So what we're going to do is we're going to have our route table with a default route to the internet gateway. That's the existing one. However, on our private subnet, our one that has our back-end servers, we've created a brand new route table. It has no entries in it apart from the local route when we create it. We're then going to create a NAT gateway, and that NAT gateway lives inside the internet-connected subnet. And what we can then do is configure our route table from our private subnet, where our back-end servers are, to send all that traffic over to the NAT gateway, and then from there out to the public internet. And what that means is our back-end servers don't need to have public IP addresses. They never need to be reachable from the internet, and yet they're still able to reach out and retrieve those updates, those Yum repo downloads, etc. So a NAT gateway is the way that you can achieve this and then have a public and a private subnet. This is what the route table would look like in my private subnet. If you remember earlier, I had a default route that went via the internet gateway, but in this case, I have a default route that goes via the NAT gateway. And this is the mechanism where I don't need to assign public IP addresses to my private instances. Okay, what if I've created multiple VPCs and I want to connect them together? To do this, we use something called VPC peering. So a very common model for VPC peering is to create something called a shared services VPC. So this might be somewhere where you deploy things like logging servers, authentication, directory servers, those kinds of things. In the diagram here, it's VPC A in the middle. You then want to connect all of your other VPCs back to that shared services VPC so that they can consume those shared services from one place and not require you to create duplicates of every single environment. So how do you use VPC peering? Well, here we've got two completely separate VPCs. The first thing you'll notice is the IP address space for these two VPCs does not overlap. So these are two separate /16s. We have the orange VPC on the left, we have the blue VPC on the right. When we create these VPCs, though, we'd still like to be able to use security groups between them. So earlier we created my web servers, my backend servers. Well, we've got two VPCs now. We'd like to be able to refer to them across VPC peering. And we can do that. So if we have an orange security group, we can choose to allow traffic from that orange security group into our blue security group. So VPC peering works within an AWS region, enables you to connect two VPCs together, and allows you to refer to security groups between those VPCs. It can also be used cross-account within that same AWS region. So if you've separated out your VPCs into different environments in different AWS accounts, that's fine. VPC peering still works across those. What's the process to create a peering connection? Well, there's two steps to it. The first one is you have to initiate a peering request. So from one side, in this case, we're going to start with orange. We initiate a VPC peering request to the other VPC. If it's in the same account, we'll see a drop-down list of all of our VPCs. If it's in another account, you put the account number in, and you name the VPC identifier. Once we've made that request, though, even if it's within the same account, we have to accept that request. So in this case, we would go to the blue VPC, and we would choose to accept the peering request. Now, once that's done, that's a pretty good place. The two VPCs are allowed to talk to each other. But remember earlier that I said nothing interesting happens in a VPC until you configure routing? Well, the same thing is true with VPC peering. So our final step that quite often is forgotten by people, and they wonder why it doesn't work, is to actually configure the routing. So here's our route table from earlier. We've got our local entry at the top that says everything in my VPC can talk to each other. We have a route to an internet gateway, the 0.0.0 route. And we now have this third route, which says to get to 10.55, which is the blue VPC, I'm going to use my PCX, my peering connection, between those two VPCs. And when you do that, you need to configure that on both sides of the connection. So this is the entry in the route table that tells me where traffic should route if it's going to these IP addresses. Configure it on both sides, and our instances can now talk to each other, subject to their security group configuration. So what about now connecting back to our on-premises network or a remote network? We have a couple of options for doing this. We can use a VPN connection, a virtual private network connection, or we can use AWS Direct Connect. So let's explore what those two options are. On the left-hand side here, we have our corporate network. On the right-hand side, we have our VPC. Connecting these together, we have the two options I mentioned. We have VPN and Direct Connect. VPN is probably quite self-explanatory, but let's start with the building blocks that you need to make these connections. First of all, you're going to need a device in your network. We refer to this as the customer gateway, some sort of router, a device that can talk IPsec VPNs, perhaps. On the AWS side, we need something to connect to, so we're going to create a virtual private gateway. And between these two components, the customer gateway and the virtual private gateway, we're then going to build our VPN connection. Now, in AWS terms, a VPN connection is two IPsec tunnels. And the endpoints of those IPsec tunnels on the AWS side terminate in different availability zones. So by having two tunnels, you have a really good level of resilience for your VPN connectivity into AWS. Now, VPN connections are great. They work over the internet. But if you need a connection that is perhaps a bit more consistent, that is not subject to events that might happen out on the internet that might impact that connection, you might need to make this a bit more reliable. You might need to create a direct connect. So, direct connect allows you to take that virtual private gateway we created earlier and build a physical connection from our direct connect locations back to your infrastructure. So this is a 1 gig or a 10 gig connection straight into the AWS network via our direct connect locations. And our direct connect locations are in colo facilities, places like Equinix or CoreSite or Interaction. So between VPN and direct connect, you have a choice. And these are a few things you might want to consider in terms of what connectivity option is the right one for you. Both of them are secure connections into your VPC. A VPN is that pair of IPsec tunnels, gives you a good level of resilience. But with Direct Connect, you can also build two connections. You can build resilience into Direct Connect as well. Direct Connect is dedicated to you. It's a 1 gig or a 10 gig or multiple 1s or 10 gig connections straight into AWS. And the data transfer rate that we charge over Direct Connect is less than internet rates. So as a guide, in Ireland at the moment, it costs 9 cents per gig for data transfer out via the internet gateway, whereas it's either 2 cents or 3 cents per gig if you're transferring data over Direct Connect. If you're considering using Direct Connect, our advice would actually be to use both Direct Connect and VPN. That gives you a really good availability story. It gives you resilience and redundancy both to a physical connection, falling back to a connection over the internet. Okay, so we now have our connectivity back to our on-premises network. We've peered some other VPCs. What about other AWS services? How do they interact with our VPC? So we're going to talk about some of the specific AWS services that we have. We're going to talk about VPC endpoints for S3 and more recently announced DynamoDB. How does DNS work in a VPC? And finally, we're going to talk about logging with VPC Flow Logs. So let's talk about those AWS services that we've got. So an example, RDS, Relational Database Service. When you create an RDS instance, you actually choose which VPC to launch it into. And what that means is that RDS is available on an IP address that is inside your VPC. Even though it's a managed service by AWS, we present it to you on an IP address inside your VPC. Because it's inside your VPC, you can use security groups with it. So all the same principles that we just applied to our web servers and our backend servers, they apply to RDS as well. We can choose to allow traffic from our application server to our RDS environment. RDS can run as a multi-AZ infrastructure, multi-availability zone, and again, that security group extends across both availability zones and makes the configuration of the security inside your VPC very simple. When you access RDS, we actually give you a DNS name. So what that means is when you configure your application to connect to that particular DNS name, should there be a failover event between the two different availability zones for RDS, we will update that DNS name for you. Therefore, as long as your application is connecting to that RDS CNAME that we create, we will flip over to the other AZ automatically. And in amongst all of that, you don't need to reconfigure anything to do with the security groups, because it's one security group that is used to manage this. What about Lambda? You might have heard Lambda today a couple of times, I'm sure, in some of the other sessions. Well, you can have a Lambda function that is running inside your VPC. So here we have it down on the bottom left. The Lambda function runs. Perhaps it needs to be able to reach out to something like an EC2 instance that is also running inside your VPC. It can do that. It can also reach out to an RDS database. And again, we have security groups controlling this access within our VPC, controlling that traffic flow. So that gives you an idea of how two of our services interact inside a VPC. What are some of the best practices around this? Well, first of all, just consider that most of our services do support running inside a VPC. Still apply the least privilege concept with security groups, and always use multi-availability zone if available. So things like EFS, Elastic File System, we actually present you with an endpoint for EFS in each of our availability zones, and you should use those. Now, what if we want to access S3? S3 doesn't exist inside our VPC. It exists on public IP addresses. You normally access S3 over the internet. But if you're inside a VPC and you don't want to have an internet gateway, how could that work? Equally, what if you wanted to access DynamoDB, again from inside your VPC, and you don't want to use an internet gateway? Well, let's take a look at that VPC. This would be the typical setup. We've got a VPC here with two subnets. We've got a DynamoDB table and an S3 bucket sitting outside of our VPC. And up at the top right, you can see that we have an internet gateway. This is the normal traffic flow for traffic trying to reach Dynamo and trying to reach S3. Your applications are going to be making outbound connections. So one of the things that we can actually do here is remove the internet gateway and instead replace it with a VPC endpoint. So let's look at S3 specifically first. When we create a VPC endpoint, it's another object that is associated with our VPC. When you create it, you'll then be prompted to choose some route tables, just like the ones we looked at earlier, and we will automatically put an entry into that route table for you. So you can see here, this route table does not have a route out to the internet, but it does have this additional route now, this second one. And it says all traffic that is destined for this prefix list, which has a name of com.amazonaws.uswest2.s3, which is S3 is the service endpoint for S3, we're going to route that traffic via the VPC endpoint. We don't need an internet gateway anymore to get to it. The same thing applies to DynamoDB. Again, you're going to create a VPC endpoint, and when you do that, it will create entries in your root table. But the nice thing about using VPC endpoints is you can actually apply a few different policies. So from a security perspective, we actually get some extra tools by using VPC endpoints. We can apply a policy to the VPC endpoint that defines which S3 buckets we can access. So although it is an endpoint for S3, you can actually lock down exactly what the traffic is allowed to flow to from your VPC. So it can only reach your S3 bucket. Further to that, we can actually apply an IAM policy on the S3 bucket itself, which says, don't allow access to me over the internet, only allow access if it came via this VPC endpoint. So we can use these two extra security controls that we have here to manage access via VPC endpoints. Same obviously applies to DynamoDB. I wanted to briefly also touch on CloudFront. So CloudFront is our content delivery network. If you're not familiar with CDNs, it's basically a very large distribution of caching servers, or what we call edge locations, and it allows you to cache that content closer to where your users are consuming it. So this might be a static website, it might be assets that are used for displaying particular web pages, and we have many edge locations around the world. Currently we have 88. 77 of those are actual CloudFront edge locations, and the other 11 are what we call regional edge caches. So I'm not going to go into all the detail of CloudFront here, but there are two concepts I wanted to touch on. First of all, CloudFront distributions. Now, CloudFront distribution is the domain name that is used to refer to these objects that we're storing in CloudFront. Within that distribution, we then need to define the origin of these objects. So where are we going to retrieve these objects from when an end customer asks for a particular URL? It supports HTTP and HTTPS. And then beyond that, we need to configure a whole bunch of other parameters, things like origins, behaviors, to control how this CloudFront distribution works. But linking this back to our VPC and S3 that we've already talked about, here's an example of some of the origins that you could be using. So we support using an S3 bucket to store perhaps your static content. We could be reaching back to an EC2 instance that is in our VPC. As long as it has a public IP address and is reachable via an internet gateway, it can also be an origin for CloudFront. We can reach out to elastic load balancing, or we could reach out to any other custom origin that you can define using a URL. So that's where CloudFront fits in. Now, everything we've talked about so far has been based on IP addresses. What about naming? What about DNS in our VPC? How does that work? Well, actually, it's really quite simple. When you create a VPC, there's a set of options that are by default turned on. You can see them down at the bottom here. It's DNS resolution and DNS host names. If they're both set to yes, we will automatically provide the ability to resolve names out on the internet inside your VPC, and we'll also automatically assign a DNS name to every single EC2 instance that you launch. If we have a look at an EC2 instance, you'd be able to see that name displayed. But what if you don't want to use the name that we generated? Well, that's where Route 53 private hosted zones come in. You can actually create your own zone, your own domain name, that you use within your VPC. The rest of the internet can't see it. It doesn't resolve publicly. But you can create, in this case, a zone called demo hosted zone. Within that, I can create an entry for my EC2 instances, and I can point that at my private IP address. So within the world of my VPC, I can now resolve names that are within demohostedzone.org. How do we get visibility of what's actually going on inside our VPC from a network perspective? Well, VPC Flow Logs are the tool that we give you to be able to do this. So VPC Flow Logs allow you to get visibility into what is happening when a piece of traffic tries to flow within your VPC. Is it stopped by security groups? Is it stopped by network ACLs? If something isn't working, VPC Flow Logs is the tool that you can use to try and find, what have I misconfigured? What have I done wrong inside my VPC? And it also gives you a whole load of data that you can use to then do analysis on the traffic flow within your particular VPC. How do you configure it? Well, you go to your VPC. At the bottom of the screen, you'll see a tab that says Flow Logs, and it's as simple as then choosing to enable it. You create the flow log, you enable it for the VPC, but if you want to, you could just enable it for a particular network interface. In most cases, though, we see customers generally enabling it for the whole VPC. Once that's done, what do you actually get? Well, once the flow log's created, we then push that data into our service called CloudWatch Logs. So you end up with raw log data, and it looks like this. Within that log data, you've got the standard details of that particular packet. So we've got the fact that in this case, it was rejected. So a security group or a network ACL has denied this traffic flow. We know which port it was, so it was UDP 53, so it's DNS. We can also see what the source and destination IP address is, both of which you'd expect to be able to see in this kind of logging. So now you can investigate, first of all, what is this traffic, and then why was it blocked? Why was it rejected? So just as a reminder, let's go right the way back to the beginning. What is a VPC? Quite simply, a VPC is your private network within AWS. It's where you define the parameters of the network, everything from the CIDR range that's used, how it's divided up into different subnets, and how the routing works, both within the VPC and then out to remote connected networks. It can provide access to multiple EC2 instances inside that VPC. You can create as many subnets as you need within that VPC, aligned to those availability zones. And in terms of security, we have security groups and network ACLs. The security groups control access to AWS services, as well as other EC2 instances in your VPC. We provide flow logs so that you can inspect the traffic that is flowing from a metadata point of view. And we provide the ability to connect outside your VPC. You can create an internet gateway to talk to resources out on the internet. You can connect to your corporate data center over VPNs and direct connect. You can connect to other VPCs using VPC peering. And you can also reach out to VPC endpoints to reach things like S3 and DynamoDB. So that's been a very quick tour around the features of VPC. Hopefully you've got a bit of an idea now of how you might create an Internet Connect VPC, how you might use some of the features that I've shown you here. And I'd like to thank you very much for your time this afternoon.